Have you ever really thought about what happens when you click on something online? How a whole world of information just appears on your screen almost instantly? It honestly feels like magic. But you know what? It's not magic. It's engineering. And today, we're going to pull back the curtain and look at the complex, brilliant web that makes it all happen, using some key ideas from network engineering. Let's get into it.
So, here's our game plan. First, we'll look at the physical stuff, the literal wires and hardware that make up the internet's backbone. Then, we'll get into the internet's address book, how every single device can find any other. After that, we'll see how massive networks get sliced into smaller chunks for speed and organization. And finally, we'll get to the really cool part, the intelligence that guides your data on its incredible journey.
I mean, think about it. This is happening billions of times every single second, all around the globe. It's this constant, invisible storm of data flying everywhere. But how does that actually work? Well, by the time we're done here, you're going to have a really solid grasp of the amazing tech that powers pretty much everything we do online. Okay, so before we can even begin to talk about data packets and IP addresses, we have to start with the real world, the physical stuff. Because every bit of information you send or receive has to travel through an actual physical network. So let's take a look at how these fundamental networks are put together. You can think of a network's design, its topology, like the street layout of a city. A ring topology? Well, that's kind of like a single big circular road. If there's one accident, one breakdown, the whole thing grinds to a halt. But a star topology, which is what most of us have in our homes and offices, that's more like a city with a central hub or roundabout. All roads lead to the middle, which makes it way more resilient if one of those roads has a problem. So the big takeaway here is that there's no single best design. They all have their pros and cons. The star is great for sure, but that central hub, that's a single point of failure. And a full mesh where every device is connected to every other device, I mean, that's incredibly reliable, but it's wildly expensive and complex to set up. It's all about choosing the right tool, the right layout for the specific job. And what about those physical connections, the roads themselves? Well, the most common network cable is called a twisted pair, and it comes in two main flavors. You've got unshielded UTP and shielded STP. That UTP cable, that's almost certainly the standard Ethernet cable you've got plugged into your computer or router right now. But if you're in a place with a lot of electrical noise, say a factory floor, that extra shielding in STP becomes absolutely critical to protect the data signal from interference. All right, so we've laid out our physical network, our city map is built, but now we need a way for all the houses on that map, our devices, to actually find each other. This is where network addressing comes into play. It's basically a system of unique IDs that works a lot like the Postal Service in the real world. You know, every single time you type a website into your browser, you're using something called the Domain Name System, or DNS. Just think of it as the Internet's universal phone book. It sees the name you typed, looks up the real numerical IP address for that server, and connects you. Seriously, without DNS, we'd all have to memorize long strings of numbers just to check our email. No thank you. Now, if we go a little deeper, we find the MAC address. This is a unique ID that's literally burned into the hardware of every single network device. It's like a permanent, unchangeable fingerprint for your laptop or your phone. And it's what devices use to talk to each other directly on a local network, like your home Wi-Fi. And that, of course, brings us to the famous IP address. It's a really brilliant system because it has two parts. The first part is the network address. Think of that as the street you live on. It defines the whole neighborhood. The second part is the host address. That's your specific house number on that street. Together, they create a totally unique address for every single device online. You know, back in the early days, these IP addresses were actually grouped into these rigid classes to handle different size networks. You had Class A for the absolute giants, Class B for big companies, and Class C for small businesses. Now, this exact system is pretty much history. We use much more flexible methods today, but it's still a really important concept to understand how the internet was first designed. So you've got a really big network, like a huge city, but what if you want to create smaller, more organized neighborhoods inside that city? Maybe one for the sales department, one for HR. Well, that's exactly what subnetting is for. It's this clever way of taking one big network and slicing it up into smaller, more efficient, and more secure subnetworks. And why even bother doing this? Well, subnetting solves some huge problems. For one, it cuts down on a ton of unnecessary network chatter, which really boosts performance. It makes the whole network way easier to manage. And maybe most importantly, it improves security by keeping any potential problems contained in one small neighborhood instead of letting them spread everywhere. Okay, now let's build on that with an idea called route summarization. Yeah, the process on screen looks a little complex, but the core idea is actually beautiful and simple. It's like instead of giving someone the exact address for every single house in a neighborhood, you just give them the zip code. For the internet's routers, this means they can advertise one single simple route for a whole bunch of networks, which keeps the internet's roadmaps small, fast, and super efficient. All right, this is where it all comes together. We've built the physical roads, we've created the address system, but now we get to the most amazing part of this whole story. How does one tiny packet of data navigate the entire global internet to find its destination in less time than it takes you to blink? The answer is all about the intelligence of devices called routers and the protocols they use. I want you to picture a router as the super smart, super fast traffic cop standing at an intersection of a dozen different superhighways. It looks at the destination address on every single data packet, instantly checks its map, and points it down the absolute best route. It's doing this job millions of times a second, and it's what keeps the entire internet from becoming one giant traffic jam. So how do these routers even get their maps in the first place? Well, there are two main ways. With static routing, a network admin has to manually type in every single route. That's fine, I guess, for a tiny network that never ever changes, but for the internet, no way. That's where dynamic routing comes in. The routers literally talk to each other, sharing information to build and update their own maps on the fly. It's like a self-healing system that can adapt to changes in real time. So RIP was one of the very first dynamic protocols, and it was pretty simple. Its only goal was to find the path with the fewest number of routers, or hops, to get somewhere. But it was limited. Its replacement, RIPv2, was a huge step up. It added support for something called classless addressing, which is just a fancy way of saying it was much more flexible with IP addresses. It also added security and became way more efficient. But the modern internet demands even more intelligence. And that's where OSPF comes in. OSPF is basically like having a GPS for your data. Instead of just counting the number of turns, it builds a complete map of the whole network and then calculates the absolute fastest path based on things like connection speed or bandwidth. It's the powerful engine behind so many of the world's biggest corporate networks. And then you have EIGRP, which takes things even further. This is a super powerful hybrid protocol that looks at a whole bunch of factors to find the best path. It's like having a 5-star travel agent who doesn't just find the fastest route, but also considers delays, how reliable the path is, and even how busy it is. This lets it make incredibly smart, fine-tuned decisions about where to send your data. So after all that, which one is the best? OSPF, EIGRP? Well, the truth is, it depends. Just like there isn't one best way to build a city, there's no single best way to build a network. It all comes down to picking the right tool for that specific job, based on things like size, speed, and budget. And that really is what network engineering is all about. So from the physical cables running under our feet to the complex algorithms that guide our data in milliseconds, the internet is just a modern marvel of engineering. But as our world gets exponentially more connected, what's the next big hurdle? What new challenges will we face? And what incredible new technologies will we have to invent to solve them? It's something to think about.